Okay. Good morning, everyone.
Good morning, sir.
So today is Friday, so it's the last lecture of this week. So let's see. Are there any questions from what we discussed last time? So what we did last time was to prove this theorem, which says that if there is no f incrementing path, then the flow you have is a maximum flow. In particular, you can find a cut whose capacity is equal to the value of the flow. And that implies that this is a maximum flow, right? And this theorem and what we proved previously, which was the easy direction of this theorem, together, this implies that in any network, the value of the maximum flow is equal to the capacity of the minimum cut. And that is called the max flow min cut theorem, right? So this is the max flow min cut theorem. Okay, good. And you see, although we did not explicitly discuss an algorithm, in some sense, we already found the algorithm, right? What's the algorithm? Can anyone tell me? Supposing you are given so what you are given is a network N where the directed graph is D with source S and target T and capacity function is C. Then your goal is to find a max flow, a max ST flow, and to certify. How do you certify that a given ST flow is maximum? You find a minimum cut of the same capacity, right? Our goal is to find a maximum flow and a minimum cut. Right? And of course, because this is a max flow and a minimum cut, it will be the case that the value of the flow is equal to the capacity of the cut, right? So this can be thought of as a certificate, right? How do you convince someone that a flow is maximum? By giving them a cut of the same capacity, okay? So although this is a maximization problem and not really a decision problem, you can still have the notion of a certificate. How do you know that something is maximum for a certain optimization problem? And this is one example. And here the certificate is to give a cut of the same capacity. So what is the algorithm? Can someone tell me, based on our discussion so far, what is the algorithm to find a maximum flow and a minimum cut?
So you look at the underlying undirected graph and you
Okay.
find an S and you look at the ST paths
Okay.
and then you check if any of them is F incrementing.
Okay. Fine. So you're saying that at every step, no matter, so there is, I mean, we are not going to have the full algorithm, but the basic idea is that every step you find an F incrementing ST path, right? And if you are able to find such a path, then you will be able to get a better flow. And when you are not able to find such a path, then your algorithm stops, right? And you find a cut of the same capacity. So of course, there are details we need to work out. How do we find such a path? But let's not worry about that. This is, let me not call this even the algorithm. Let me call this the method, right? Because we are not going to go into complexity and everything because we still have some details to be figured out. Okay. So the method is start with any flow. We will come back to this in a few seconds. Okay. So start with any flow F. And now you search for an f incrementing st path p. Okay, if such a path exists, then obtain a new flow f prime by adding p to f. Okay, so I'm going to be vague here. What I mean by this is, um, we had this theorem earlier, this proposition. Okay, so you found a path p, and now you define f prime in this manner. Okay, so that's what I mean by vaguely. Abusing notation to the maximum extent possible, use proposition. Okay, and now you set f to be your flow f prime, and you go back to this step. Okay, and when such a path does not exist, if such a path p does not exist, find an st cut k, st die cut k, such that the capacity of k is equal to value of the flow f, and return the flow and the cut. Okay, and what do I mean here? Here I am referring to the theorem that we discussed. Okay, so the theorem actually tells you what this cut, how you can define this cut. Again, remember, we are not looking into implementation details or the algorithmic details, right? This is the general method, and we still need to make it precise by discussing how to find a path and how to find this cut and everything, right? So refer to above theorem. Okay, good. So there are some details to be worked out here. First of all, how can we start with any flow? Does the graph have a flow? Does the network have a flow? What if the network does not have a flow? Or is this not possible?
Initialize it to 0, sir.
Exactly. Put everything to 0, and that is the 0 flow. So this is not a problem, right? Every network has a flow. Just put f of each arc equal to 0, and that satisfies the capacity and the conservation constraints. Okay, so this is not a problem. So, for example, you may start with the 0 flow. Okay, and that just means that f of a equal to 0 for each arc a. Okay, good. So now the big question is, how do you search for an f incrementing st path? Okay, if we know how to search for an f incrementing st path, then we are done. Okay, and whenever the search algorithm does not return an incrementing st path, we know that there is no more f incrementing st path. So this is basically the main point to discuss, and this is related to how to find an st die cut. Okay, so now the next goal is to search for an f incrementing st path. Okay, so it turns out that this is actually not difficult. One just needs a small trick and it gets the job done. So remember, what is an F incrementing ST path? Let us revisit this. So it is an ST path in the underlying undirected graph, right? So it means that it is not a die path. It could have some forward edges, some backward edges. Okay, something like this. So can someone remind me what is an F incrementing ST path? Pappu, can you hear me? Pappu, can you hear me? Okay, so what do the forward arcs have to satisfy? This is a forward arc. What does the forward arc have to satisfy? I'm reading what you're typing, so you can type if your connection is not great. What is capacity? What does the forward arc have to satisfy? Supposing this arc is A, then can you write to me an inequality that needs to be satisfied by this arc? What is the condition that a forward arc needs to satisfy for an ST path that is F incrementing? Under what circumstances can I increase the flow? If you're not sure, you can write not sure, that's okay. Are you sure it is less than equal to? Because that should be satisfied by any flow. So that is nothing special. Are you sure it is less than equal to? Okay, thanks. So this has to satisfy f of a less than c of a. And can you also tell me what the reverse arcs have to satisfy? So this is a reverse arc. And what does a reverse arc have to satisfy? Greater than 0. Okay. Thank you. Good. Okay. So everybody remembers this, right? We need the forward arc to satisfy this condition, and we need the reverse arc to satisfy this condition. So these are the two types of arcs that we are interested in. So what we will do is we will use this information, the definition of an F incrementing ST path, to construct a different graph, a different directed graph. Okay. So what we will do in this example, so our flow is in red color. The flow is F and the graph, the network is D. So what we will do is we will construct a different graph with respect to this flow. We will call this the auxiliary digraph. With respect to this flow. So I will call it df. Okay. So it depends on the flow f. Can anyone tell me how we should define this auxiliary digraph? Remember, the two types of arcs we are interested in are the arcs that satisfy this condition and this condition. But these have to be the forward arcs and these have to be the reverse arcs. So how should we define this directed graph, the auxiliary digraph? And I will tell you what we want. What we want is the following. Our goal is to construct an auxiliary digraph df such that each f incrementing ST path in the network N corresponds to an ST dipath in the auxiliary digraph F DF, and vice versa. So this is our goal, right? What we want to do is, rather than finding an F incrementing ST path, we want to reduce the problem to finding an ST dipath in a directed graph. And that can be done by breadth first or depth first search. So that is easy. Okay, you should already know from a basic graph theory or algorithms course. Okay, so our goal is to construct this graph so that every F incrementing ST dipath becomes an ST dipath in this graph. Every F incrementing ST path becomes an ST dipath. How should we do that? Can anyone tell me? Is the goal clear? Is it clear what we are trying to get at?
Yes.
Okay.
So,
So you
we
have, yeah,
can
go ahead.
add residual edges such
Okay.
that if we have an edge with a flow f in the forward direction between two vertices, we can add an edge with capacity equal to f in the reverse direction. So if you have an edge from u to v with flow f, then we can edge with capacity. We can add an edge with capacity from v to u with a capacity from v to u with a capacity of f. Sorry.
I have a question. So we are just trying to construct a digraph. There is not going to be any capacities in the new graph, right? So this is just a digraph. So do you want to slightly revise what you are saying? I don't want any flows or capacities or any kind of weights, any kind of numbers associated with arcs of this digraph.
Okay. So then we can just have, whenever there is a flow greater than 0, we can just have a reverse edge over there.
Okay. Okay. So whenever you're saying that, whenever the flow between two vertices, let's say, let's just look at an example. Let's look at this guy here, S to V1. This is greater than 0. So what should I do in this directed graph?
Oh, okay. So if it's full capacity, we need to remove that edge. Yeah.
Okay. But should I put the reverse arc?
Yes, we can put the reverse arc over there at
Right,
least.
right. So we can put the reverse arc. So let's do that. This flow is greater than 0. So we'll put the reverse arc. Okay. And here the flow is equal to the capacity. So we cannot send any more flow on this arc. So we will not put the forward arc. Is that correct?
Yes, yes.
Okay, good. Now let's look at, I want to look at something more interesting. Let's see what happens here. What do we do here? What do we do between V3 and V4?
You can put a reverse arc because from V4 to V3 because
V4
you
to
have
V3 reverse arc. Okay. And what else?
and yeah, that's it.
Okay. So this is for this arc, right? This is full capacity. So we put the reverse arc. But what about this guy?
Oh, it has 0 flow, right? So you cannot put a forward for that.
Okay.
But you can put, and you already have put a reverse. So
Right. But I can put a second one, right? No, nothing hurts me. To be
okay.
consistent, I could just include both arcs.
Yeah. Okay.
Okay. What about this one? Can someone else tell me? What do we do here? What do we do in this case? From S to V3. Don't worry. If it is a bit vague, it's okay. It's all right to be confused as to what is going on. We will write down everything formally in some time. What do we do with this arc? The capacity is 4, the flow is 3. What should I do here? I want someone else to respond. I'll start calling out names. Samuel, are you there?
Yeah,
Yeah, what do you think we should do here?
you should have a forward and backward arc.
Forward and backward. Because the
Yeah.
flow is less than the capacity, so we can send more flow. So we put the forward arc. Because it is a positive number, we can also put the reverse arc. Okay? Good. So this is the case with any arc where the flow is positive and is less than the capacity. So that is also the case here, also the case here. So let's see. So in both of these cases, we will have both possible arcs. Okay. Can someone tell me what happens between V1 and V2? Let's see. Muathasim, are you there? Abdul? Rebin, are you there? Okay. What should I do between V1 and V2? Can you tell me? Do we put a forward arc? Do we put a reverse arc? Do we put both arcs? Okay, so by reverse, you mean in this case from V2 to V1? So the flow on V1 to V2 is 0. So we can push more flow because V1 to V2 is 0 and that is less than the capacity 1. And this is at 1. So we could send it back. Right? We can't push more flow in this direction, but we can send it back. Right? Okay. And finally, what happens here? This is already at full capacity, so this can only be sent back. And this one, 3, 4, is both directions. Okay? Does everybody agree with what we have? I think I may have made some mistake in copying things. Let me see. This is 1. No, this is fine. Okay, good. Okay. Okay, now you can notice that every f incrementing st path here will become an st dipath in this graph. And every st dipath in this graph will become an f incrementing st path in the original network. Okay? Just think about how we are constructing this graph. Okay? Is it clear how this graph is being constructed?
Yes.
Are there any questions from anyone?
Here we are checking if for a forward arc, if the
Yes.
capacity is full, and also the second constraint, are we checking that? Means for the S to V1, I'm saying.
Okay.
As the capacity flow is equals to capacity,
Right.
so here we are, because of that, here we are constructing a reverse arc or what?
That's right. Because the flow, because the flow is equal to capacity, we cannot put the arc S to V1 because it is already equal. So we cannot push any more flow. So the intuitive understanding is if an arc is already at full capacity, let's say from U to V, so U is the tail and V is the head, then you cannot push any more flow on that arc. Okay, so you will not put the arc UV in the auxiliary graph. But because the flow is greater than 0, you can pull back that flow. You can sort of reduce that greater than 0 quantity, right? Because all numbers have to be non-negative. So because it is greater than 0, you are able to reduce it. And so you can put the reverse arc.
Oh, because of the second constraint. Yeah.
Exactly. Right?
Yeah.
Okay.
Yes.
Good. Okay, so let's write down the formal definition, just so that it's crystal clear what we are doing. So we construct the auxiliary digraph df as follows. So first of all, I will just put it as in bracket. The vertices of df are the same as the vertices of the original digraph in the network N. Okay, so the vertex set is completely obvious. What is not completely obvious is the arc set. So the arc set is defined as follows. U to V. So when I write like this, I mean U is the tail and V is the head. Okay. U to V is an arc of the auxiliary digraph if and only if one of the following happens. Either UV is an arc of the original digraph and the flow on this arc U to V is less than the capacity of this arc UV. Okay? Or VU is an arc of the directed graph and the flow on VU is greater than 0. Okay? So this is exactly how we constructed our auxiliary digraph.
So for the second condition, shouldn't it be f of u to v?
Let's see.
When you're adding a reverse edge.
Right. So we are adding the arc from U to V. Right. In our directed graph in DF, in the auxiliary graph, we are adding an arc from U to V. So the two cases are either this was already an arc, like 1 comma 2, for example. The flow was 1 and the capacity was 2. Right. In this case, we will add this arc. But the other possibility is that you had an arc like this, and this was a positive number. And so again, in the auxiliary digraph, you can add the reverse arc. So both of these conditions will lead to an arc like this. Notice that here we are looking at U to V. So either this arc already existed in the digraph and the flow was less than the capacity, or we had the reverse arc in the digraph with a positive flow. And so now we can send it back. Because it is positive, we can put the reverse arc. Instead of VU, we'll put UV to send it back. Does that make sense?
So here vu belongs to a of d and f of uv should be greater than 0, right?
No, because we don't even know if UV belongs to A of D. We don't even know whether UV belongs to A of D. Let's take an example. So let's go back to this example here. Okay. So consider why we put this arc in this directed in the auxiliary graph. Right. In this case, what happened is there was no arc in the original graph going from V1 to S. So we did not add it because of the first reason, right? This is not the reason that is applicable. This is the reason that is applicable because the reverse arc was in the original graph. So notice that here, SV1 is there in the original graph and the flow value on that arc is greater than 0, which is why in the auxiliary digraph we put an arc from V1 to S.
Yes, sir, it's clear.
Yeah, does that make sense?
Yes, sir.
Okay. So we don't even know if the UV exists in the original digraph, right? Okay, so this is how you construct the digraph. And there is an observation which I want you to prove on your own or convince yourself, whatever you like, which is just that we have achieved our goal. Every F incrementing ST path corresponds to an ST die path in the directed graph, in the auxiliary graph. Okay. Good. And why is this good? Because now, instead of looking for F incrementing ST paths, we just look for ST die paths in the auxiliary digraph. Okay? And clearly the auxiliary digraph can be constructed in polynomial time, right? You look at each arc and you figure out which arc should be added to the auxiliary digraph, right? And finding an ST die path in a digraph you just need breadth first search or depth first search, right, for directed graphs, and that is going to be order M. So finding an ST die path takes time order of M. And if you can't find an ST die path in a directed graph, then you will be able to find an ST die cut in the directed graph. I will leave this to you as an exercise. Apply the breadth first algorithm and see how you will get an ST die cut if you cannot find an ST die path. Exercise. Prove that if DF does not have an ST die path, then DF has an ST die cut that is empty. What I mean by that is, what will happen is you will find a partition of the vertex set. This is the directed graph F. S will be here, T will be here, and there will be no edges going like this. No such edges, arcs. No such arcs. In other words, partial plus of X should be the empty set. Okay? That is what I mean by an ST die cut that is empty. There are no arcs in that set. Okay, so the exercise actually starts here. And you also need to, this might even be on the assignment, I'm not sure. I'm still to prepare the assignment. Okay, so you will find an ST die cut that is empty. Show that such an ST die cut may be found in polytime. And I am already giving you the hint. Use just use breadth first search, depth first search, and prove it. Okay, it's quite easy. And the point is, if you find such an ST die cut in the auxiliary digraph, then in the original network, it will correspond to a die cut with the properties that we have already discussed. Remember this claim? If you find an ST die cut which is empty in the original auxiliary die graph, then you'll go back to the original die graph, the original network, and you will observe that the same cut, the same set X will satisfy these two conditions. Okay? So the point is that if you can't find an ST path, then if not, then you will find an ST die cut K such that the capacity of K is equal to the value of the flow F. Okay? Good. So the point is, we have basically discussed how the algorithm can actually be implemented in polynomial time. But not really. There is one problem. There is one problem. Can anybody tell me that what is the problem?
We must prove that it will terminate after a finite number of path finding. For example, we won't keep going on and on and on.
Okay. Okay. Good. Supposing I tell you that all the values are integers. Supposing I tell you that all the capacities are integers. Then will it terminate? So there is a more fundamental question that you are asking. Will the algorithm terminate? So let's forget this one. Okay? Let's ask the more basic question. Will the algorithm terminate? So let me simplify it. Assume that all capacities are integers. Now will it terminate?
Yes,
Yeah. Why?
because every time you find an F incrementing path, you're increasing the value of the flow. So it increases by at least one. And we can
Right.
bound the maximum flow it can have by the sum of the outgoing edges from S, outgoing arcs.
Right. Okay. Yeah. So in fact, the point is that if all capacities, yeah, so that's one way to put it. Another way to put it is that if all capacities are integers, there is another way to say this, integral. Okay. So what I mean is by that if the function C is integral, then what will happen is that you start with the zero flow or any flow that is integral, doesn't matter. And now you find an incrementing path. Remember the computation of epsilon. In the computation of epsilon, you are always using integers. Either you're subtracting one integer from another or you are taking an integer number, right? So epsilon will always be an integer. And so the value of the new flow will always increase by epsilon, which will be at least 1 because it is going to be a non-negative integer, right? So you always increase the flow value by 1. And therefore, you will have an integral flow and the algorithm will terminate in as many steps as the maximum flow value. So if the maximum flow is 10, then you will have to terminate in 10 steps because you start from zero flow and then at each step you will increase by at least 1 because epsilon will always be an integer that is at least 1. Okay? then the algorithm will terminate in, let's say, value of f steps where f is the maximum flow. And another point that should be noted is that this will be integral. The maximum flow itself will be integral since all capacities are integers. This is not obvious. This requires a proof. And that is an exercise. It may or may not be on your assignment again. Okay? But for now, trust me and think about it later. Okay? And the proof is very similar to things we have already proved. So you should think about, supposing you have a maximum flow which is not integral, okay? Then you will have an incrementing path because it is, okay, sorry. If it is a maximum flow, then let me think about this. Okay, so what you do is you assume that the maximum flow is not integral, okay? But you take a flow that is maximum while being integral. So you take as large a flow as possible that is integral. But you are assuming by contradiction that this is not a maximum flow, okay? So that means that there has to be an f incrementing st path. And now you try to get a contradiction from this point, okay? So that is an exercise. It might be on your assignment. So you might already want to start thinking about it. Okay, so the point is that the algorithm will terminate in these many steps. Also notice that if all the capacities are rational numbers, then you can multiply by some big rational number and get a different network where all the capacities will be integers. Okay, so by dealing with integers, in some sense, we are also dealing with rational numbers. The problem is irrational numbers. So the answer to this is actually no. If we allow irrational numbers, and I will not be discussing this in this course, partly because our interest is in graph theory, and in graph theoretical and most of the real world applications, irrational numbers do not arise very often. Okay, but otherwise the answer is yes. Okay, so it is yes for rational numbers, and that is just because you can multiply by a big integer to make all the capacities integers. Okay, and then you apply the argument we just discussed. Okay, so the complexity of the algorithm is order of m times the value of the maximum flow. Because in each step you will increase by at least one, and at most, and each step requires order m time because you are doing a breadth first search or a depth first search to finding a st dipath in the auxiliary digraph. Okay, so the algorithm that we discussed has this complexity. Okay, and this algorithm is called the Ford-Fulkerson algorithm, which many of you may have seen in a previous algorithms course. From what I understand by talking to Meghna is that in that course, she did not cover how to get it down, how to get rid of this value. Remember, this can be very big. You could have a maximum flow of value 1000. And so in some sense, this complexity does not depend on just the number of vertices and the edges. It actually depends on the value of the maximum flow, right? And that could be a very big number. So in the next lecture, we will discuss how to get rid of this point, and that is called the Edmonds-Karp algorithm. Edmonds-Karp, and there is another person who did it. I forget the name of the person right now. So if I remember correctly, this is order m square n. Okay, this will be in the next lecture. I want to discuss something very important, so please stay back for a few minutes. I'm going to stop recording because I don't want to have this part recorded. Okay.